Until now, we assume that the transmitter, receiver, and everything else in the environment are stationary. We want to see the effect of phase on the path length. So a carrier wave caused by FCT is impinging on the mobile antenna in a parked car in this example. This wave arrives tau seconds later. What is this tau? The path length divided by the speed of electromagnetic wave, d naught over c, when nothing is moving. Now imagine that a car is driven at a constant velocity of v meters per second, opposite to the antenna. Electromagnetic wave, which was covering a distance of d naught, now has to cover a distance of d naught plus vt. d naught plus vt. Taking the t as common, we can say that the carrier frequency has changed. And there is a Doppler shift in the actual carrier frequency, which is given by v over c fc, and the minus sign appears because the direction is opposite to the antenna. Another perspective to see this is that Doppler shift is a percentage of carrier frequency given by the ratio between the velocities of the car and the electromagnetic wave. For a general angle of arrival phi, instead of this negative sign which comes from cos pi, we have cos phi. Now we will see why Doppler shift is a deceptive villain. If car is moving with a velocity of 260 km per hour at fc equals 1.9 GHz, the Doppler frequency comes out to be just minus 105 Hz. This is so small that even a simple PLL would easily track it down. On the other hand, for a comparison, a plus minus 20 ppm crystal at 1.9 GHz can generate a carrier frequency error of 76,000 Hz. Compare this value with the Doppler shift. Why is Doppler shift so important then when it can easily be recovered with a PLL? For this we have to add multiple paths. Assume that there is a birdhouse at the end of the road and a multipath copy arrives reflected from the birdhouse. So direct path is still given by d naught plus Vt. The multiple path arrives after d naught plus Vt plus drb minus Vt, because this is the distance it has to cover first and then comes back, drb minus Vt. So total distance d naught plus 2rb minus Vt. The important point is that now there are two carrier waves arriving at the receiver. One with a Doppler shift of minus v over c, the other with a Doppler shift of plus v over c. When these two are added on the receiver antenna, from the sum rule of sinusoids, we know that we can write the sum of two sinusoids as this product. And from here we can see that it is actually a very high carrier frequency on the order of gigahertz multiplied with a very low frequency, something like this, on the order of hertz. So the low frequency component rides on the high frequency component and creates crests and troughs, just like a beating effect of two waves. So as an example, this is the direct path at frequency fc minus ft. This is the reflected path at frequency fc plus ft. And we can see a slowly varying envelope that is riding on the carrier wave now. This is the envelope that actually drowns the signal.
This is a little demo I have constructed to show the effect of Doppler shift in the case of continuous waves. This flow graph is pretty simple. We have the sample rate and the Doppler shift of path 0, the Doppler shift of path 1. The display points are just for this oscilloscope. So there are two signal sources. One is a real cosine waveform with the frequency 100 plus Doppler path 0. The second is also a real cosine waveform with the frequency 100 plus Doppler path 1. And they are adding at the receive antenna. Let us see what happens. So here we can see that the arriving multipath are separately shown in the top plot while the received signal is shown in the bottom plot. They are overlapping each other because both Doppler shifts are 0 from path 0 and path 1. Let us impart a slight Doppler shift to one of those paths, the direct path. And we can observe that there is a pattern emerging of crests and troughs. When the two waves they add out of phase, we have a trough. And when they add together in phase, we have a crest. This is how Doppler shift in a way modulates the envelope of. He set the two values at positive and negative extremes so that we can have a magnified view of this effect. And here we have it in phase addition, and here this is out of phase addition. Next, we will move towards the effect of shift on the actual data waveform. Let us study the effect of Doppler shift on the waveform carrying the data. The excess bandwidth is defined as zero point 0.5, and we have 32 samples per symbol. The maximum Doppler shift is 1000 Hz. We have a sample rate of 40K and the carrier frequency of 10,000. Then instead of only delay and amplitude, we have a Doppler of path 0 as well. Similarly, we have, in addition to amplitude and delay of path 1, we have the Doppler of path 1. We have chosen two paths instead of three so as to clearly see the effect on the waveform. The bits are input to a QAM waveform baseband block, which we have made ourselves. Let's change the parameter so that they take the values from our own variables instead of the default ones. Now, this waveform is input to two up converter blocks, one with carrier frequency plus Doppler path 0, the other with the carrier frequency plus Doppler path 1. I made these blocks myself, and until now we have been pretty clear on how to make these blocks. There is a paired source, and then we convert it to float and give it to two signal sources. Multiply INQ, subtract, and so on. If I would have done this here, the flow graph would have become too messy, and that's why we use these. The delay of direct path, the delay of the first multipath, and similarly their amplitudes. They are being added at the receive antenna. The power is being normalized, and here we are observing them through an oscilloscope and a spectrum analyzer. Let us run the flow graph and see how this behaves. Here you can see that the amplitude of path 0 and path 1, the delay of path 0 and path 1, and the Doppler of path 0 and path 1 can be controlled through these sliders. And here we have the waveform. The arriving multipath will be shown here. Their summation at the antenna will be shown here, while the transmit and receive spectrum are here. In this case, the amplitude of path 0 is 1, the amplitude of path 1 is 0, so we can only see the direct path and its spectrum. The first thing we do is change this value to 1 as well, so that both the direct path and the multipath have equal power. This is something that helps in visualization, and then we forget about the amplitude. I'm not changing these delay values because we have already covered this in the section on delay spread. Let us start with the time domain wave. We can see that the peak to peak value has changed due to both paths arriving in phase and having the same Doppler shift. Let us change the Doppler shift to a value, let's say 4 Hertz. And now we can starting to see the carrier waveform, which is coming in phase and which is going out of phase. And here, this is due to the Doppler shift. We have to differentiate what effect is due to the Doppler shift and what is due to the delay spread. So this 0 is due to the Doppler shift, while this one is due to the waveform itself. And here it goes completely out of phase. To see the enhanced version of this, let us change this Doppler shift to a negative values so that we can, and now they will be are adding in phase. And then one thing I want to change is the spectral width. So let me change the symbol rate so that we have a wider bandwidth. Simple, instead of 8 might be a better value. Yes, 8 is better. Let us set the amplitude of the first multipath to 1. And now see what happens when we slightly change the Doppler shift. The main point I want to show you here is that the spectrum is not much different, especially in its spectrum, in its width. And when they are adding in phase, they are adding in phase for several symbols. When they are adding out of phase, they are adding out of phase for several symbols. This is what we call slow fading. On the other hand, if I change this to a large value and this one to another negative large value to enhance the effect, now you will see that they will be coming in and out of phase within a symbol time. This is also visible from the spectrum here. If you look here, one spectrum is shifting to the left due to the negative Doppler shift, the direct path. The other spectrum is shifting to the right due to the positive Doppler shift, and their spectral contents clearly have increased the bandwidth at the receiver. We have said the spectrum has widened a lot. This is called fast fading, and its effect on time domain is that within the same symbol, the waveform from the first and the direct path, they add in phase and out of phase. This is analogous to delay spread, where the time domain of the direct path was clearly lagging behind the time domain waveform of the first multipath. And after their separation becomes an order as some function of the symbol time, we were saying that the frequency selective fading was occurring as compared to frequency flat fading. In this case, we say it's a slow fading as compared to fast fading. Play around with these values and you discover many new concepts.
So we conclude that if there is just one path, Doppler shift acts exactly like a carrier frequency offset, not a problem. When there are two paths, the envelope with FT is superimposed on the carrier wave in the form of a product. Overall envelope rises and falls according to the frequency of this slow wave. However, when there are multiple paths, each with its own Doppler shift depending on the direction of arrival, then a random pattern of peaks and values is created. And the car entering into this random pattern exhibits different level of fades that depend on the movement of the car, of the receiver, and of the surrounding objects. The system has to be very carefully designed to recover from the fades that occur with the motion. Just analogous to the wireless channel in time domain we saw earlier, here we will see the frequency domain signals and we will assume that the channel is linear frequency invariant, which means that the Doppler shifts of each paths are occurring at a constant velocity. When that happens, we can say that the channel response consists of two impulses in frequency domain. The first path is arriving with the Doppler frequency of ft1, the second path is arriving with the Doppler frequency of fd2, and the final signal is the superposition of those two paths. Doppler spread then signifies the difference between the Doppler frequencies, and it is a dual to delay spread, which is evident from this figure. Doppler spread is third out of four fundamental quantities of a wireless channel. Coherence time is the inverse of Doppler shift, and it is a duration over which the time varying amplitude can be approximately assumed constant. For example, if this is the baseband signal, it can be assumed to be riding on two separate carrier waves, each with its own Doppler shift. Superposition of these two modulated waves creates crests and troughs, and the duration over which the channel can be assumed approximately constant is the coherence time. This is very similar to what we saw in the case of coherence bandwidth, and this is the fourth out of the four fundamental quantities through which a wireless channel is categorized. This brings us to slow and fast fading. Slow and fast fading are also known as time flat and time selective fading because they are very similar to frequency flat and frequency selective fading in time domain. For example, if the multiple Doppler frequencies are arriving such that the Doppler spread is not very large, then we can see that their superposition creates a resultant signal that does not vary significantly with time and maintains the modulation symbols overriding the carrier wave. We say that the coherence time is larger than the symbol time. However, if the Doppler spread is large between these paths, then their superposition creates a resultant signal that, in addition to this modulated data, undergoes random crests and troughs and suffers from deep fades. We say that the coherence time is less than the symbol time. Therefore, channel is not constant from symbol to symbol. Here the channel was constant for a large number of symbols.